right, hi everybody. So today we're going to do a lecture over accuracy versus precision and also percent error. Make sure that you get your metric conversion worksheet turned in. It does need to be colored. Again, you can color it in on Google Classroom, that's fine. But it does need to be colored. Make sure you circle the correct answers and you should be good. All right, so today we're going to talk about section 2.3, which is about using scientific measurement and how there is a big difference between having an accurate measurement versus a precise measurement, and then also how there is error in everything that we do. So how do we calculate what is the percentage of error in our experiment? Okay, so what is the difference between accuracy versus precision? So a lot of times you'll hear those two words used interchangeably, like, oh, it's a super accurate measurement, or, oh, it's a very precise measurement. And we generally think they're the same thing, but there is actually a big difference between the two. So when we want to talk about something that is accurate or have accuracy, it refers to the closeness of measurement to the correct accepted value. So let's say we're measuring the density of something and we get the density of the object to be 4.26 grams per milliliter. And we're like, oh, okay. So it's 4.6 grams per milliliter. Great, fantastic. Well, we get another measurement of our own, and let's say we measured it as 4.56 grams per milliliter. Well, that's pretty accurate because they're pretty close to the same number. If we got something more like 4.2 grams per milliliter, that accuracy starts to decrease. It's getting a little bit further away, so we can't say it's that accurate of a number or a measurement. We could say instead, maybe it would be more precise. So it's more of a precision or precise measurement. That refers to the closest of a set of measurements to one another. So that means if I had, let's say, 4 measurements, and let's say I had, let's go back to our 4.6 example. I had 4.6 grams per milliliter. I had 4.55 grams per milliliter, 4.61 grams per milliliter. I would say those are pretty precise numbers. They're all 4s, and they're all pretty close to each other. So that would be precise. If I had another example where it was like 4.6 grams per milliliter, 3.2 grams per milliliter, and then back to our 4.61 grams per milliliter, I would say this guy right here would not be precise. He is not close to these two numbers whatsoever. But these two, those ones definitely could be precise. Now, would they be accurate? That depends on what we're measuring. If we said it was back to that 4.6, yeah, it would also be precise, inaccurate. So, the big difference between accuracy and precision. Accuracy is dealing with closeness to the correct or accepted value, while precision is looking at all of the measurements and are they close to each other. So, oops. There we go. True or false? The following measurements are both accurate and precise if the accepted value is 3.70 grams. Okay, so we have to decide, is this accurate and precise? So we look and we said our actual given value is 3.70 grams. So that means for it to be accurate, all of our measurements need to be close to this number. For them to be precise, they all need to be within each other or close within each other. So we have 3.24 grams, 3.21 grams, and 3.223 grams. Well, we look and compare them to our actual value. I would say I don't think it can be accurate because it's not close to that 3.70 grams. But the numbers themselves, they're pretty close to each other. So I would say it would be precise, but not accurate. So let's check our answer. That is true. So it would be false. It is not precise and accurate, but it could be precise because these three numbers are very close to each other, but not accurate because they're not close enough to the actual accepted number. All right. There's a really good video that's linked on Google Classroom on my slides. So if you still have more questions on accuracy versus precision, I would take a look at that. You can jump over there once you're done filling in your notes so you can have that. But there is a way to have either low precision with high accuracy, or we can have high accuracy, low precision, or low of both, or high of both. So let's use this example. We're going to go play darts, okay? And ideally, we want to be this person. We want to have high accuracy and high precision. High accuracy because the goal is to make a bullseye. So we want to be close to the bullseye with high precision, meaning all of our darts end up in that spot. So that would be high accuracy and high precision. Now, if you were more like me, when I play darts, I have low accuracy and low precision because I'm not anywhere close to the bullseye and my darts are ending up all over the place. So that would be low accuracy, not close to the bullseye, and low precision because they are not close to each other. You can have high accuracy and low precision as it's close to the bullseye, to each other, but they're still too far apart from each other to say they are precise. Or we can have the opposite of high or low accuracy but high precision, where you're not even close to that bullseye for accuracy, but all of your darts end up in the exact same place every single time. So we can have one without the other. Again, accuracy, right where you want to be on target with your actual value. Precision, they are all lumped together. All of your numbers are very close together with minimal separation. Okay, so that's the difference between accuracy and precision. Now let's talk about percent error, because every time we do an experiment, there's always going to be some sort of error. There's something that pops up that's going to affect the overall experiment in some way, shape, or form. Whether it is environmental, whether it is mechanical error, or something. Again, we're humans, we make mistakes. The environment is not perfect all the time. Little things pop in. So we came up with this equation called percent error. So we just want to figure out how much error is within our experiment. When I was in college, we used to have to solve for percent error after every experiment to figure out what, if it was a high number, what happened, what could have been those issues that caused a very high percentage of error. Or if it was super low, that told us, well, we did a pretty good job of keeping our area clean and maintaining our environment to have the best experiment possible. So we have this equation, and you will need to know this equation. Percent error equals the value experimental minus the value accepted divided by the value accepted times 100. The shorthand version of that is VE for value of experimental minus the value accepted, VA, divided by VA times 100, just to turn it into a percentage. Now, there are times you're going to get a negative value and a positive value. The negative value is the accepted value is greater than your experimental, meaning the value that you come up with is smaller than what you actually got in the experiment. A positive value is the opposite. If the experimental value is greater than the accepted, so what you measured is bigger than what is actually accepted in the problem. Now let's run through a problem real quick. So what is the percentage of error for a mass measurement of 17.7 grams given the true value is 21.2 grams? So just like what we did in our density problems, we're going to list everything out, write down what we know, and then plug it into our equation. So what is the percentage of error for a mass measurement of 17.7 grams? So that's telling me that I measured the mass to be 17.7 grams. So that means my VE, my experimental value, would be 17.7 grams. And it says the true value, or the also known as the accepted value, is 21.2 grams. So that's what I know. So now I can plug it into my equation, and again, your equation is percent error equals VE minus VA divided by VA times 100. So it would be 17.7 minus 21.2 divided by 21.2 times 100. Now, when you plug this into your calculator, you're going to have to do 17.7 minus 21.2 and then hit equals, because your calculator doesn't like to follow order of operations very well. Then you're going to take that answer that you just found, divide it by 21.2, hit equals again, and then times that by 100. When you do that, you should get an answer of 16.5%. And that'll be your final answer. So there's no grams, there's no meters, liters, whatever. You just kind of cross off your units, and then you're left with just a percentage. So 16.5% error. Overall, that's not horrible. It's not great, meaning there's solidly something that happened in there, whether your scale's off, whether maybe you didn't read the measurement quite close enough, maybe there was leftover chemicals, or, something was wrong there that caused a 16% error. Ideally, you want to be closer to the smaller number, so 5% would be great. When I was in college, I think we couldn't have anything over, I believe, like 13%. Otherwise, we were going to have to redo the lab. So the smaller the number, the better results you are getting from your experiment. Okay, let's do one more. So a value measured experimentally as 4.26 milliliters. What is the percent error given that the correct value is 4.15 milliliters? Again, we're going to write out our equation so we have it with us. Percent error equals VE minus VA divided by VA times 100. Okay, so let's figure out what's our VE, what's our VA. So a volume measured experimentally, big hint there, experimentally, tells me that's going to be my VE. So VE equals 4.26 milliliters. And what is the percent error given that the correct value, also known as the actual VA, of 4.15 milliliters? So I have my VE, I have my VA, now I can plug it in. So I'm going to take 4.26 minus my actual 4.15 divided by 4.15 times 100. And again, when you plug it into your equation, it should be 4.26 minus 4.15 equals. Then go divide by 4.15 equals times 100. When you do that, you should get an answer of 2.65%, which would give you answer D as the correct answer, which turns out to be true. All right, your homework for tonight. This is actually going to be due on Thursday because tomorrow we're going to do a kind of a lab called the Mini Metric Olympics. We're going to start it tomorrow. We'll finish it up on Thursday. So this worksheet is due Thursday. It's accuracy, precision, and percent error worksheet. Make sure when you do your percent errors, I need to see your work. So just like what we did here today in the notes, this is what I should see. I need to see it. I can't read your brains. I can't get in there to see how you did these equations. I know it's kind of tedious, but I need to see it. Again, I will take off points on quizzes and tests and homework if you do not show your work. So just get in the habit now of showing your full work. If you have any questions on the homework, shoot me an email or come see me Wednesday morning. I will be in. So by all means, stop by and let me know if you have any questions. Have a great rest of your day. I will see you tomorrow.